Hi, and welcome back to the second part of today's lecture entitled Line Integrals of Vector Fields and Work. So, in the first part of this lecture, we have seen that the work done by a force field in moving an object along a curve C can be written out as a line integral of f dot dr over the curve C. And we have shown two methods on how to evaluate such line integrals. So, on this second part, we shall now be applying these formulas here. Okay, so to start, we have this example. Suppose we have the vector field F to be the force field that acts on an object that moves along this curve C, and the curve C is parameterized by this parametric equations x is cosine t and y is sine t, with t ranging from values 0 until pi. So we want to evaluate the line integral of f that dr over that curve C. So recall the formula that we have from the first part. So what we'll do here is to use the parameter t and rewrite f as a vector valued function in terms of that single parameter t and replace dr by r prime dt. So we now have the line integral to be equal to the integral from t running from 0 until pi. F would now be written out as such. So x is cosine t, so x squared is cosine squared t, and y is sine t, so negative xy would be negative cosine t sine t. Then dotted with dr would be replaced by r prime dt. R prime is given by negative sine t cosine t dt. So next we get the dot product between these two vectors. The dot product is simply negative 2 cosine squared t sine t. And to integrate this, we'll just use substitution. We could let u be cosine t so that its derivative is negative sine t. So based on the knowledge that we have from Math 21, that integral would just be equal to 2/3 of cosine cubed t, which we evaluate from 0 until pi, and thus giving us a final answer of negative 4/3. So the work done of this force field in moving an object along the curve C, parameterized by this curve, which is actually a circle, but only from t running from 0 to pi, is given by negative 4/3. So next, here we have an example that wants us to find the line integral of f dot dr over the curve C, where f is given by this vector field z, y, x, and c is the line segment from the point A, which is negative 2, 1, negative 3, to the point B having coordinates negative 1, 5, 0. So what I will do first would be to find a parameterization for the curve C. So this one would be an easy parameterization for our curve, but notice that our curve runs from A until B, so we should have the correct direction for our parameterization. So once again, we'll be using the formula that we have. We will write f in terms of t using this parameterization. X is negative 2 plus t, y is 1 plus 4t, and z is negative 3 plus 3t. So the integral of f dr over c can now be written out as the integral from 0 to 1. Then z will be replaced by negative 3 plus 3t, y will be replaced by 1 plus 4t, and x by negative 2 plus t. Then we have dotted with dr. dr is r prime dt. R prime is simply, sorry, here, R prime is simply the vector 1, 4, 3. So 1, 4, 3 dt. And once again, we do the dot product, then simplify, and eventually this, we have the integral from 0 to 1 of 22t minus 5 integrated with respect to t, which could easily evaluate, that is equal to 11t squared minus 5t, which we evaluate from 0 to 1, giving us a final answer of 6. Okay. Next. Next, we have an example wherein we want to compute for the amount of work done by the force field F, which is two-dimensional, having components 2y minus x, 2y minus x, and xy, in moving an object from the point 0, 0, which is the origin, towards the point 4, but along this curve C here, which is parameterized by t squared 2t. Okay. So note that the point 0, 0 corresponds to the vector 0, 0, which is r of 0, and the terminal point 4, 4 corresponds to the vector r of 2, which is for with so that our parameter would have a value of 2. So t here runs from 0 until 2. Okay. So in computing for the work done is again equal to the integral f dr over our curve c. And once again, using the formula that we have the integral from 0 to 2, then f can now be written out as 2y minus x will be replaced by 4t minus t squared. Then xy would be replaced by t squared times 2t or 2t cubed. Multiplied by dr, dr here is given by 2t, 2 times dt. And once again, we do the dot product, multiply by the first components, then multiply the second components, then add them. So doing the dot product, we get this scalar field or this usual function in terms of one variable. Then we integrate that with respect to t. So the integral of 8t squared with respect to t would be 8 thirds t cubed, and the integral of 2t to the 3 would be 2 fourths or 1/2 t to the power 4. Then evaluate from 0 to 2, and we'll get the final answer to be 88 over 3. Okay. So since there is a relationship between line integrals of vector fields and line integrals with respect to the variables x, y, and z, which we have learned from a previous lesson, the following properties of line integrals of vector fields are inherited from the said integrals. So first, changing the direction of the curve would be equivalent to multiplying the original integral. So we have here the original integral, we multiply it by -1. That's why when we're parameterizing the curve C, we should be aware of the direction of our object. Moreover, again, the parameter that we'll be using should be increasing from the initial point until the terminal point. Second, if C is a piecewise smooth curve, that is, C can be written out as a union of smooth curves, for example, C1 until Cn, then the line integral of f dr over that curve C can be written out as the sum of the line integral of f dr over each of these each of these curves here. So over C1, over C2, and until over Cn. Then we just add up all the line integrals that we have. So again, this is because the integral is just a summation, a limit summation, and of course, limit summation are all linear. So we shall use this second remark for our last example. So for the last example, so suppose here we have f given by x squared y and x, and we want to find the line integral of f dr over the curve C, where C is the triangular path shown below. So we have a triangle having vertices at the origin, at 1, 0, and at 1, 2. So notice that this curve C here is piecewise smooth. It is the union of C1, C2, and C3, where C1 is the line segment from the origin to the 1, 0, C2 the line segment from 1, 0 to 1, 2, and lastly C3 to be the line segment from 1 to back to the origin. So the line integral of f dr over C is the sum of this respective line integrals here. So we'll be computing each line integral separately. So for C1, so this is just a horizontal line segment. We can easily parameterize it using this R1 parameterized by T0 with T running from 0 to 1. C2 is a vertical line segment from this point towards that. So you can easily parameterize it by this parametric curve 1 to t, with t again running from 0 to 1. And C3 from 1 to going to 0, 0 can be parameterized by r of t equal to 1 minus t, 2 minus 2t, with t running again from 0 to 1. So note that these parameterizations are not unique, but regardless of the parameterization that we'll be using, we can obtain the same value for the integral as long as, of course, the integration is correct and the direction of our path is also correct. Okay, so for the first line integral, the line integral of f dot dr over c1. So this is c1 and this is our force field f. So x would be replaced by t, y by 0. So f can now be written out as 0t, 0t. Then you have dr to be the vector 1, 0 times dt. Then integrated from 0 to 1. So dot product, the dot product is just 0. So the integral of 0, of course, is just 0. Next, for c2. So c is parameterized by this. So here, x is equal to 1, y is equal to 2t. So f can now be written out as 1 squared times 2t, or 2t, then 1. So 2t, 1, then dr would be 0 to dt, 0 to dt. Then do the dot product is just 2, and the integral of 2 would just be 2t, which we evaluate from 0 to 1, having a value of 2. So lastly, for C3 is parameterized by this. So x is 1 minus t, y is 2 minus 2t. So f here, first component x squared y, can now be written out as 1 minus t quantity squared times 2 minus 2t. And the last component will be 1 minus t. So we have here, okay. Then solving for dr is r prime is negative 1, negative 2 dt. Then doing the dot product, so dot product, and simplifying, we'll get this integral. Then evaluating that integral, we'll get this. So next, evaluating that from 0 to 1, we get negative 3 halves. And lastly, so to get the integral of f dot dr over curve c, we just add the three values that we have. 0 plus 2 plus negative 3 halves. And the work done, the total work done in moving the object along C by F is given by 1 half. And there you have it. So that is the end of our lecture on line integrals of vector fields and its application in solving for the work done. So I hope you guys have learned something from this, and remember that this video has a counterpart discussion video where more examples will be solved using the methods that we have enlisted so far. So see you guys again in the future lesson. Bye for now.